Hello and warm greetings to all of you. I hope and wish that each one of you, along with your family, is able to stay safe and healthy amongst this pandemic. So, as you can see, as Shubha had mentioned, the topic of our presentation is of today's webinar is mechanism modeling using rigid body mechanics principles. So, I'll just in brief tell you about the agenda. So, the agenda is we are going to understand the concept of degrees of freedom of a mechanism, and then we are going to demonstrate uh, mechanism modeling by using first principles over a loader machine. And the objective of this webinar is to learn building an optimally constrained mechanism model from first principles, and we are going to showcase its application in performing structural finite element analysis. Let me quickly start the presentation. So let's understand what is a linkage. So a mechanical linkage essentially is basically an assembly or a combination of uh, two or more than two rigid links which are interconnected by joints. So the objective is to uh, get a controlled output motion in response to an applied input motion. So if you see that basically two types of mechanisms, one is an open type and the other one is a closed type. So to cite an example of an open mechanism, you can look at the upper limb of your body, which comprises of your hand, your forearm, and your upper arm. And basically, you can see the connection between your hand and your lower arm to be the wrist, and then the connection between your lower arm and your upper arm is your elbow, and the connection between your upper arm and your the body is basically the shoulder. So you have three rigid bodies getting connected by you know three joints. So that essentially gives us the different degrees of freedom, which or the different motions which we can execute using our upper limb. And an example of a closed mechanism could be, as shown in the figure, this is a three-bar mechanism, or you can even have a slider crank mechanism. Moving on, so let's understand the concept of the degrees of freedom, which is very, very important. So what do we understand by degrees of freedom of a rigid body? So those are essentially number of independent movements which are possible. So in the case of any rigid body in a three-dimensional space would be six. So there would be three translation degrees of freedom and three rotational. And when we talk about degrees of freedom of a mechanism, as we saw in the previous slide, it's essentially a combination or an assembly of different rigid bodies which are interconnected by joints. So, so the definition of a degree of freedom of a mechanism is basically obviously the number of independent parameters which could define its configuration. So like in the case of an open mechanism, which I talked about, if you consider your body, so whatever degrees of freedom or whatever the movements you can execute independently using your upper body limbs is essentially its degrees of freedom. Whereas in the case of a three-bar mechanism or a slider crank mechanism, it is one. So mathematically, how do you define your degree of freedom? So it is six times your number of rigid links comprising the mechanism minus the number of degrees of freedom which gets restricted by your joints and the degrees of freedom which get restricted by your boundary conditions. So that will give you, your total degree of freedom of a particular mechanism. Now let's look at what do you mean by a rigid link? So rigid link, as I told you, any rigid body will have 6 degrees of freedom. So you can see in the figure over here. So if you consider these two particles, each particle will have 6 degrees of freedom each. So so they would have in total 12 degrees of freedom, and you have a rigid link between them. So the purpose of this rigid link is to apply constraints, and it will apply 6 constraints so that the total degree of freedom of this system becomes 6. And so any tool which you use for modeling will essentially have different sort of these rigid links. They will have separate names. So the purpose of those links is essentially to provide to constrain the degrees of freedom, so that in total they end up with 6 degrees of freedom, which are three translation and three rotational. The other sort of link is an hydraulic cylinder. Now hydraulic cylinder essentially is similar to a rigid link, but in the only difference being that this axial translation degree of freedom is released over there, so you have that degree of freedom available for a hydraulic cylinder. So that's why it has 7 degrees of freedom. So in addition to 3 translation and 3 rotation, it will have an additional translation DOF along its axis. So in this figure, you can see, so this outer box is basically the cylinder head, and this is your piston rod, which is going to move in and out of this. So this can elongate or compress depending upon the situation, and this is how and any axial force is going to get transferred. And the way to connect it with the rest of the mechanism is using ball joints. So these red balls basically denote those ball joints. And apart from this, these ball joints, you should have either end should be actually the actual rotation should be constrained at one end. And this is how I mentioned, this is free to move in this direction. Now let's look at the different joints which are possible. So ball joint, we all know it will have 3 rotational DOFs. All the translation DOFs are basically getting constrained when we have a ball joint defined between any two bodies. If you have now, let's consider a slot joint. So slot joint will have 3 rotational DOFs and 1 translational DOF available. So if you look at this figure comprising of link 1 and link 2, so by lateral I mean this particular direction. So it will have a translation degree of freedom available in this direction. So it only restricts 2 degrees of freedom. And your hinge joint basically has 1 degree of freedom available. So no translation degrees of freedom are available. Only 1 lateral rotational degree of freedom is available. And in any bodies, if you see bodies around you, how they are connected, they are basically connected at 2 ends. So the way to model is using a ball joint and a slot joint combination. So here, the red dot depicts your ball joint, whereas here the yellow dot depicts the slot joint. Now let's look a particular mechanism over which I'm going to apply these principles. So this is a simple loader mechanism. So let's see how many rigid bodies this mechanism comprises of. So this is the frame, the yellow portion which you see, this is called the frame. These orange parts are called as the boom slabs. So I'm basically considering them to be one body because they are essentially connected together through this cross tube. So they basically form one body. Then you have a bell crank, you have a bucket link over here, and you have a bucket. So this mechanism is getting actuated through 2 boom cylinders, which are on either side of the mechanism. This is the bucket cylinder, and you have 2 steering cylinders. Now let's understand this mechanism further. So it essentially has 5 rigid links. As I told you in the previous slide, one is the loader frame, the boom slabs plus the cross tube. So the cross tube gets welded onto the boom slab. So that's why it can be considered to be one rigid link. We have a bell crank, we have a bucket link, and we have a bucket. So it has 5 rigid links. And we have 5 hydraulic cylinders. So these are the 2 boom cylinders on either side. Then we have a bucket cylinder in the middle, and we have 2 steering cylinders. So one easy way to figure out degree of freedom of any mechanism is to count the number of hydraulic cylinders which are in series. So these 2 boom cylinders are in parallel. So the purpose of having 2 cylinders in parallel is to share the forces or the loads. The degree of freedom which it will provide is going to be a single degree of freedom. So both the boom cylinders basically provide only 1 degree of freedom to the mechanism. Then you have a bucket cylinder which will provide another degree of freedom. And again, these 2 steering cylinders will provide the 3rd degree of freedom to the mechanism. So that is the easiest way. If somebody asks you, how do you find out the degree of freedom of a particular machine by merely looking at it? So this is the way you can compute the degree of freedom. Now this is what I mentioned. So it essentially has 3 degrees of freedom. So one is the bucket elevation. So I have animations towards the end of the presentation where you can have clear view of these degrees of freedom. So bucket elevation, where this bucket is essentially going to move up and down, and that is maneuvered by these 2 parallel boom cylinders. Then you have bucket rotation. So this bucket rotation, the bucket can rotate about this particular pivot point. So the joint between the boom slab and the bucket, and that is called a bucket rotation, and that gets executed through a bucket cylinder. And then you have a loader articulation. So these steering cylinders basically help in rotating this entire machine about a vertical axis. So that is called steering, and we call it as a loader articulation. Now let's look how we have modeled these different geometries using simple rigid elements. So you can see how the loader frame gets modeled. And over here, what I've used is all those connection points. So connection points are the pivot points where, the points where which a particular body is getting connected to other bodies. So basically, we make points at those pivot point locations and join them together to constitute a single body. So this is how the loader frame was made, and this is how we have made a rigid body model or a 1 degree model of boom slabs and cross tube. Now bell crank, bucket link, and the bucket. Now let's look at the total degree of freedom. So for an unconstrained mechanism, because we have 5 hydraulic cylinders and each hydraulic cylinder will have 7 degrees of freedom. So total DOFs provided by hydraulic cylinders is 35, whereas you have 5 rigid bodies and each rigid body having 6 degrees of freedom. So they add 30 degrees of freedom. So any unconstrained mechanism will have 65 degrees of freedom. Now let's look at the links, which how these links are assembled by joints. So these are the different joints which have been used, like a hinge joint, a slot joint, ball joint. So let's look at them in detail. So now there's a hinge joint defined between the loader frame and your boom slabs. So this is the ball joint and a slot joint. So in a previous slide, we saw that a hinge joint essentially can be modeled using a combination of a ball joint and a slot joint. Let's look at the next joint. So this is between the cross tube and the bell crank. So this is your cross tube, which is rigidly connected to your boom slabs, and you have a hinge joint defined between the bell crank, which is this green part. And again, we are using the same, strategy of using a ball joint and a slot joint to model it. Next one is between the bell crank and the bucket link. So this is your bucket link, and we have another, through ball joint and slot joint, we are modeling it. Now let's look, between the bucket and the boom slabs, you have these yellow dots representing 2 slot joints. Then we have in the middle, we have a ball joint basically, which connects the bucket to the bucket link. Now let's look how, the hydraulic cylinders, so if you look at this, this is your bucket cylinder, which is getting, connected through ball joints at the end, but it will have another, axial rotation getting connected at either of these ends. Now you have these boom cylinders over here, which you can see. These are the boom cylinders which get connected through ball joints to the loader frame and to the boom slabs. And again, you have these steering cylinders which get connected to the same, ball joint, plus one axial rotation is getting connected to the loader frame. So if you sum all these constraints, you'll get 51 internal constraints. Okay, let's look at the boundary conditions. So these are external constraints which we are applying. So by external constraints, I mean the bodies. So this mechanism basically will get connected to other body parts which we are not interested in modeling. So we basically replace them by their joint constraints which they apply on this mechanism. So one boundary condition is between the steering hydraulic cylinders and the external. So this is how we are doing it. So this is akin to a ball joint because we have constrained all the translation degrees of freedom over here. Now we have, between the loader frame and the external. So there's a hinge joint basically. So again, using suitable, translation degrees of freedom constraints, I'm applying that hydraulic joint condition over here. So as you can see, translation along Z is free and rotation around Z would be free. So that's how it's going to articulate. So total, if you add them up, the total external constraints come out to be 11. Now let's look at the kinematic validation. So by kinematic validation, I mean whether I'm able to, generate the desired mechanism motion which I want out of this machine. So let's look at the degrees of freedom of this mechanism. As we saw, the unconstrained degree of freedom are 65. So that is, the combination of hydraulic cylinders and the rigid links. That is 65. We saw that in the previous slide. Then we have 51 internal constraints and we have 11 external constraints. So they add up to 3. So as we said in the initial slide that the degrees of freedom of this particular mechanism would be 3. So we have been able to capture that correctly. Now let's look at the bucket elevation. So now in order to realize a bucket elevation, we are going to lock the bucket cylinder and the steering cylinder. And let's see how this motion happens. So this is the bucket cylinder. Bucket elevation is happening through your boom cylinders. So the boom cylinders, as you can see, they are rotating as well as they are elongating. So hydraulic cylinders are basically, the purpose of having an hydraulic cylinder is to actuate your mechanism. So this is, here we see how the bucket elevation is getting actuated through boom cylinders. Now let's look at the other one. So the next degree of freedom is the bucket rotation. So in order to have a pure bucket rotation, we can keep either boom cylinder locked and either steering cylinder locked. We need not lock both of them because that will lead to over constraint. As I said, any hydraulic cylinders which are in parallel, so kinematically they provide only 1 degree of freedom, and the whole purpose of having uh, more than one such cylinder is to share the load. Now let's see what's happening over here. Again, this is how the bucket rotation happening, and you can see this bucket cylinder, it's elongating and rotating, and through its actuation, you can see this bucket rotation happening. Now let's look at the third degree of freedom, which is loader articulation. So in this again, we are going to lock either boom cylinder and the bucket cylinder. And here you can see this is how the loader is articulating or rotating about a vertical axis. You can see these steering cylinders. One of them is getting extended, whereas the other one is getting compressed, and they are rotating about the external points. And this is how the entire mechanism is able to articulate. So we have so in this way we have been able to capture the correct degree of freedom of a mechanism. Now this is an important exercise because most of the times what happens is especially in an industry, you simply use the tool to blindly model your mechanism, and people start applying constraints just to run the simulation. So they don't develop that insight as to what degree of freedom have to be captured and how they're going to be captured, or they apply more they maybe over constrain the model. So by over constraining the model means that we are applying more internal constraints than what is needed, and because of that your system basically becomes statically indeterminate. So you have more number of variables than the equations from rigid body mechanics, and you cannot uh, get a unique value for the forces of all those unknown variables. So for that it is very, very important that your mechanism has to be optimally constrained and you're capturing the correct degrees of freedom. So the next step is to do a kinetic or a force analysis. So we have two conditions. One is the dig load. So you can see, on the bucket teeth, basically you have loads getting applied in the Z and X direction. So these are the values. And we found out, so the purpose was to find out the loads coming on to, so this body is going to remain in static equilibrium. So whatever disturbance is produced by these external forces, uh, they have to be balanced by the cylinder forces. So let's look at the cylinder forces getting developed. So boom cylinders, the ones over here. So correctly we are seeing equal forces getting developed. So essentially the purpose of having multiple boom cylinders has solved, because if there would have been only one boom cylinder, the entire force, that is the summation of these forces, would have been getting transferred to only one boom cylinder. So here we see that they are, as expected, we are able to divide the forces amongst both the boom cylinders. And then you have a force of some force coming in the bucket cylinder. So this is how the system comes in equilibrium as expected, because there is no force acting on the system that causes a moment about the z axis. That's why you see the steering cylinder forces to be zero. So one way to understand is that because of these forces, what could have happened is this bucket could have either rotated about this axis, or it could have, this entire system could have rotated about the loader frame. And those are basically, in order to lock them, you basically have to actuate your boom cylinders and the bucket cylinders. And they would bear all the loads to keep the system in static equilibrium. Now let's look at one of the lateral load. So here is a corner pry load where there would be, in addition to these X and Z forces, there would be a lateral force also getting applied. So here we see that now, because there's a lateral component of force coming in, so that would cause a moment being produced about the Z axis. So in order to counter that and to keep the system in static equilibrium, we'll have steering cylinder forces coming, and they, as expected, they are equal. So this is how the force in the steering cylinder basically balances out the moment being produced by the lateral component of the corner pry load. So again, this is one of the verification process. So initially, first we did the kinematic validation, and now by performing by a kinetic analysis, we have validated that whatever we are expecting out of the system is we are able to achieve that. Now let's look at how this particular methodology or approach can be applied to do a structural analysis. So in structural analysis, basically we try to figure out the structural integrity of the different components of interest. So we try to find out the stress and strain coming on to the different body parts and whether they are within the acceptable limit or not. So now there are two approaches of doing it. So one way is you just, so what these solid bodies which you are interested in, you can plug them in mechanism. So you can replace the rigid uh, rigid bodies with the solid bodies, and you do a structural analysis. Or a smarter way is you can use this model, the rigid body model, and compute all the joint loads. And those joint loads you can simply apply at the ends of this body and try to figure out the stresses coming in the body. As you can see, both the approaches essentially they give you the same results. So as I said, first approach is a typical approach where you just replace your rigid body with your solid body in the mechanism, and the second one is where you just consider your solid body, and on the joints you apply the relevant joint loads which you derive out of the kinetic analysis which we saw in the previous slide. Now this is for the other load, which is the corner pry load. Again, the same methodology. And here you can see again, both these approaches are giving us the same results. So this is a comprehensive way of validating your work, because we have built an optimally constrained mechanism model. We have seen how it works, whether it's able to satisfy the degree of freedom which it is meant to do. And then we are doing a force analysis. And then eventually, once we are satisfied with our model, then we proceed with the structural analysis. Now let's look at the different benefits. So by following this approach, we are developing a very good or a comprehensive understanding of the mechanism. We are building an optimally constrained model. We are able to look at how the motion happens. So essentially, if you work mainly in a static case, you won't be able to see how the machine basically moves. So when we do a kinematic validation, by doing a motion simulation, we are able to do that. We are having a feel of how the machine or the mechanism works. Then we are able to through the kinetic analysis, we are able to extract the loads coming onto the different joints between the bodies. And the fifth one is we are able to perform a very simplified structural analysis. Yeah, so that's it from my side. Thank you.